So the previous time we talked about mean field theory, and basically we found the free energy for different types of Ising model type systems. And before that we talked about a little bit about phase transition, mostly for like 1D, 2D types models, and we didn't say much about what happened in this phase transition. We just say like, oh, you can either have or don't have phase transition for some type of system. So this time we're going to actually talk about what happened during the phase transition. So we're going to use something called Landau theory. So this is only for mean field, basically. So we have some general form of the free energy, and next to the transition point, close to the critical temperature, basically the theory is going to help us to understand what's happening in the system. So when we talk about phase transition, we have two types of phase transition in general. We actually have more, but we don't even mention the rest. So you have first order phase transition. So PT is phase transition. I'm going to write it a lot, so yeah, I'm lazy. And second order. So first order phase transition is the more like daily phase transition. I don't know, like water into ice and stuff like that. So what happened is that you look at the free energy versus some order parameter. So in our case, usually the order parameter is magnetization, but you don't have it in first order, so I'm just going to write general order parameter. And you look at the free energy. So if you look at temperature T smaller than the critical temperature, you're going to have something with some minimum point. And then you start to increase the temperature, and then you go to T that's larger than the critical temperature, and then it's become flat with another minimum. So you just go from one minimum to another. So this is like water, ice. The second order phase transition, which is what we're going to talk about. So you have the free energy again versus the order parameter. In our case is m, so I'm going to use m. So if we look at the temperature below the critical temperature, we're going to have two minima, something like that. It's like they're both like symmetric. So the system going to choose basically randomly one of those. This was called spontaneous symmetry breaking. And we increase the temperature until T equal to T dt, until it's get like this flat bottom. And then when we get above the critical temperature, this becomes like a parabola type function. So we have one minima, usually it's 0. So every time. So when we talk about Ising model, mean field, or Ising model in general, but specifically in mean field, we start in like high temperature, so we have this disordered system, some of the spin up, some of the spin down. We decrease the temperature until we go below the critical temperature, and then the system become like ordered. So you have like either all of the spins up or all of the spins down. it's going to choose randomly plus or minus finite magnetization. So this is what we're going to talk in the context of random theory. So for some given form of the free energy, so the free energy is going to be function of the order parameter, which we call m. Sometimes you can, like, some books call it like phi or something like that, depends on like the context. Which is the magnetization and the temperature. So what Landau claimed is that around the critical point, you can expand the free energy. You remember that we got the free energy last class? It was like some weird, complicated function with hyperbolic function and local and stuff like that. So he said that around the critical point, so t is around t critical, we can write this function as an expansion of, like, so we have f0, which is a constant, plus a of t m squared plus b of t m to the power 4 plus higher orders. So a of t is that. So a of t is in general some general function of the temperature, but again, around the critical temperature, this is approximately a0, t minus t critical. So we just have like Taylor expansion with only even orders. We're going to talk a bit later about why we have only even orders. And so this is the general form of the free energy. And from that free energy, we can describe some specific parameter of the system, which is called critical exponents. So we have some qualities of the system, like the specific heat, the magnetization, and stuff like that. And in general, they have very complicated behavior. But close to the transition points, they have this power law behavior that is characterized by some universal exponents. So we have the magnetization that go like T to it's called beta, where T is like it's called reduced temperature, I think, and it's defined by T minus T criti over T criti. So this is how the magnetization depends on the temperature. There is another one for how the magnetization depends on the magnetic field, if there is a magnetic field. So this is H to 1 over delta. You have the specific heat. So right here. That is T2 minus alpha, and you have the susceptibility that is T2 minus gamma. So that's susceptibility. And those are the four. I think in general you can have more, but those are those that known in the context of like what we're going to do.
Yeah, this is a general case.
Yeah, so that's like as general as it can be for second order phase transition. And the specific values of alpha, beta, and so on are going to be depends on the system. So I think in class with Vido you found beta for like normal Ising model, and it's half. And what we are going to do first is to take the example that we saw last tutorial with where you have like the question I took from the test. So you have this complicated free energy, and we're going to show that we're going to get, so it's a spoiler, but we're going to get the same value for beta in that case.
If we talk about the first order transition, and we want to talk about critical exponent, how it's...
Yeah, so first order, it's like its own thing, and like we're not going to talk about it here. I only showed it in the beginning because later when we're going to talk about what are the conditions to have second order, we may see stuff that look like they have phase transition, but it's actually first order, so you know the difference. Okay?
רגע, אבל BT לצורך העניין, איך הוא נראה?
What?
איך BT נראה שם? יש שם נעלה חופשית?
It doesn't have specific condition. In our case, it's going to be constant. Maybe. Depends on the system, but we don't see it. Yeah. So, last tutorial we got, that was 2019. So, 2019. I don't remember which question it was. So we got the free energy. I a bit simplified it because otherwise it will be like just too long to solve it. But like, you know, this is close enough. So we got J m square minus 1 over beta log of 2 parabolic cosine of J. I have to erase that. Okay, so this is the free energy, and we want to find beta, which is the exponent that relates to the magnetization. So, how are we going to do it? So, usually for those stuff, you can have like more than one method to do stuff, but you usually can use some like algorithm, which is the first step is always going to be to rewrite it as a Taylor series. That way we can actually use the Landau theory. And we want to find the critical temperature, and then we want to find the actual exponent that we're looking for. So let's do that. So we usually want to go until like fourth order, because you remember we only had even orders in the free energy expansion. So the first order would be like the second with M, and then the second one going to be the fourth order. So we don't need to go usually higher than that, but we can go lower than that, because otherwise we won't be able to do stuff. So I'm not going to do all of the Taylor expansion, but the Taylor expansion of cosine, it's like you can do it like 2 to the 4, and then you have like, you know how to do Taylor expansion. Usually at that stage, the students ask about the test. So if that will be like specific problem, I can ask you though to like add like Taylor series to the test or something. But like, yeah, because I also probably don't remember all of the stuff. So if we do a Taylor series of everything here, we get, I happen to pre-prepare it. So 2 over beta log of 2 minus 5 over 4 beta j square m square plus 41 over 96 beta cube j to the power 4 m to the power 4. Plus higher order. So that's it. So another thing you can do, if you not like you don't have time to do it or something, you can just say that like you have, instead of like those coefficients here, you just have some constant like a, b, c or something, because the actual values of the coefficient is not needed for the solution. So we're going to see that like that's always an option for easier solution. Okay, so we have this is the constant, so we call that f0.
Can you explain how you make this equation?
From here to here. This is just Taylor expansion around small m. And, sorry, I took the magnetic field to be 0. I didn't have to, I could do it in like the next stage, but this is just easier that way. Okay? So we know that around the critical point, the magnetization go from 0 to something that's not 0, so we can always assume that like we expand around the transition point, we expand around 0. So we're going to have also the coefficient that depends, like this a coefficient, that's going to multiply m squared. So this is going to be a of t is j minus 5 over 4 beta j squared.
איך אדם ממש צריך לשדה להיות אפס עוד פעם?
Because we're going to do it next stage, so I just did it here. Because around the critical point, I want to see how it's dependent on temperature, not on the field. We can like check one of them every time. So we know that around the critical point, this coefficient is equal to some constant t minus the critical temperature, right? So if t equal to the critical temperature, this equal to 0. So if I want to find the critical temperature from here, I just compare that to 0. So we have, I need another marker. So we have j equal 5 over 4 beta critical j square. Reduce j, so overall the critical inverse temperature is equal to 4 over 5 j.
So זהו אחד נקודות, נכון?
Yes, so B critical is 4 over 5j, which means that T critical is 5j over 4. This is awesome.
מה שעשית לפני המעבר לשורה אדומה, חיפשת את ה-F0, ואז צמצמנו ב-M?
No, not F0, A, the thing that multiply M squared. Because we said that in general, F is, we have some constant plus A of t M squared plus more stuff, and we know that A of t is 0 where t equals to the critical temperature.
ולאן נעלמו ה-M'ים? M's, where are the M's?
M is here. I just wanted to find the critical temperature, and we're going to choose from it here.
Okay.
I just set that to 0.
Oh, okay.
So we have the critical temperature, and now we want to find the magnetization around this critical temperature. So what we're going to do is that we're going to take the derivative of the free energy and compare it to 0. So that's going to give us the minimum of the free energy, which is what we want, and from that we're going to extract n.
יכולנו רק לצמצם ב-A0 עוד פעם?
Sorry?
איך יכולנו לצמצם ב-A0? כאילו פשוט היה
We didn't. Who is A0?
כאילו כשאנחנו אמרנו J שווה 5 ואם בטא C, J בריבוע, אז...
Yeah, all of that equals 0. I set that equals 0.
Why?
So
Why?
because we know from Landau theory that this coefficient, that A of t, which is the coefficient that multiply m square, is 0 where t equal to the critical temperature. Okay, this is like a given thing. Okay, I think I need to, I'm going to erase that. We don't need that anymore. So the derivative of the free energy over m is going to be, so F0 is constant, so we don't care about that. Now we have, I'm going to use A of t in the derivation for convenience. So we have 2 A of t multiplied by m, and then 4 multiplied by 41 over 96 beta cube J4 m cubed, all of that equals 0. Approximately, because I ignored higher order. So that equation have 2 solutions. One is m equals 0, but this is the trivial solution, so we don't care about that. And for the other solution, we have 2A of t equal to minus 41 over 24 beta cube J4 m squared.
למה בעצם אתה נגזרת?
The derivative equal to 0.
What? Only because of this you make
What?
למה עשית אבל נגזרת?
I want to find the minimum. I know that the minimum of the free energy, not to find the minimum of the free energy, I take the derivative and compare to 0. And that's going to give me the magnetization that follow the minimum.
ובשביל למצוא את TC, למה הפכת את השבר? כי זה 1 חלקי ב'?
Beta is the inverse temperature, and T is 1 over the inverse temperature. That's why it's called the inverse temperature. Basically, beta equal 1 over T.
זה בטא. It's not beta.
We have 2 beta here. I know it's horrible, but those are the notations. 1 beta is the inverse temperature, which is the beta that we have here. The other beta is the beta that we want to find, which is the critical exponent for the magnetization.
Divided by KBT.
Let's follow that.
חשוב להגיע למינימום של האנרגיה החופשית בשביל בעצם לזור את המעבר של ה-second phase of transition. בסופו של דבר, כי את רוצה למצוא הרי בסופו של דבר את הקומפוננט, את הקריטיקה לאקספוננט.
Right.
אז את עושה שם נגזרת ראשונה של האנרגיה החופשית ומאפסת אותה, כדי בעצם להגיע לאזור של ה-second order.
It's not necessarily related to the fact that it's a transition. It's just that the this is like a general equation for any value of m, and if I want to know, like the physics tell me that the m that I'm actually going to have is the m that follows the minimum of the energy. So that's the m that I want to find. Okay. So I know that it's follow that I have to follow this equation. Okay, so that's what we are left with. We have m squared here, and we have a function of the temperature here. So we know that A of t. So okay, I wrote it earlier with like regular t, so we keep it like that. So I know that that is 2A0 t minus t critical. Right? That's what we. Given. So this is equal to 2A0 t critical multiplied by small t, which is the reduced temperature. Remember? We define it. So if I go to write from like order of magnitude, because all I care about is how m depend on t. I don't care about any other coefficient. So from that, m squared is approximately equal to minus t. So the
M, it's magnetization.
m squared, yeah.
M is magnetization?
Yes.
Okay.
So, okay, so there are two like delicate points here. One is we have beta here, which is 1 over temperature, so this is actually t minus 3. But because we solved that around the critical point, so this is approximately equal to Tc minus 3, so this is just a constant. If you want to find the dependence on the reduced temperature, we have to have something that go like T minus the critical temperature. Because you see that here I cannot take T equal to the critical temperature, it will give me 0. So if I have something that's just the temperature, it's a constant. If I have something that is T minus the critical temperature, that's what give me the behavior of the transition. So I actually have only dependence on T here. So we have some factors that multiply T, we don't care about that, even that it's minus. And overall, m is proportional to square root of T, and from that, beta equal half. So this is the same thing that you got with video for like the normalizing model, and it's because the system is basically not that different. So the critical exponents are the same, but it's not necessarily always going to be like that. Yeah.
עוד פעם, מה שהדגשת, מה זה בעצם, איפה אנחנו נותנים את השוויון? לא, לא, לא. Down. Down, no? Yeah, down. Yes.
So that's all of those are equal. I just rewrote that as that. Just
לא הבנתי פשוט למה זה באמת שווה כפול T קטן.
that?
לא, ממש בביטוי האחרון, מה שאמרת ששלושתם שווים, אז בביטוי האחרון.
Oh, because the reduced T is that. That's how we defined it. So I just multiply by
אוקיי, ואז אני מסתנס, אוקיי, טוב, תודה.
אני לא כל כך מבין למה יש פה את ה... למה אם יש מינוס, כלומר שזה פרופורציונל למינוס T, נכון? אז אין צריך...
Yeah, but the minus is part of the coefficient. Like you always have, that's why you have the prop here. Like this is just, we don't care about sign, we don't care about.
אוקיי, ולמה את מחשיבה כל גורם שהוא פשוט T להיות למשל כלומר? הרי אני מבין שלצורך העניין T מאוד מאוד קרוב ל-TC בסביבה, אבל בכל זאת אני יכול להגיד ש-T זה כמו T פחות TC פלוס TC או משהו בסגנון שווה לשחק עם זה כדי לקבל משהו מהצורה של T קטן.
Because, okay, let's say I want to get as close as possible to the critical temperature. So I take that expression and I take everything to be T just equal the critical temperature. So here it's work, I have something which is very close to what I actually have. But here it doesn't work because it's just going to give me 0. So where that doesn't work, it means that I have to take the next order. Here I don't have to take the next order. I don't have a reason. I got something that's pretty good, right? TNT critical is pretty good, but if it's giving me 0, it's usually means that like, usually when we do some kind of expansion, if we get 0, we know we need to take another order.
זאת אומרת, כי את אומרת שזה יצא פשוט זניח וזה פשוט יצא שטויות מצפוניות כאילו?
I would not say that like that, but
אוקיי.
I just don't need to.
כאילו, זאת אומרת, זה מספיק קרוב כדי לחשב קבוע כששכחתי לצורך העניין, כששכחתי פחות TC זה כאילו כמו 0 כזה, אבל...
Yeah, because that's the thing that's going to change during the transition. That's also why I don't care about the minus, because it's just going to switch like how I'm looking at it.
How we get this equation in blue? M squared from how? Yes.
So, okay, so you agree that that's equal that?
Okay.
So, this one, next time I'll do it more organized, but this one is equal to this one.
Okay.
So, that's just like a bunch of numbers. So I have something multiplied by m squared, and on that side I have other something multiplied by t. and I only care about how the mathematization depends on t. So I just like, yeah, m squared is proportional to t.
כלומר, את מזניחה אותם כי הם קבועים כולם.
I don't neglect them, I just don't need them for what I was asked. If the question was find m squared around a critical position or something, yeah, sure. Like, I just need the exponents.
אז אם נסכים את זה, אמרנו שכיתרון הקבועים האלו, ה-critical exponent, זה של ה-second order transition.
Right.
אז בשאלה פה לא אמרו לנו איזה first order, second, אז איך אנחנו מגיעים, מסיקים שזה בכלל ה-second order?
Good point. So we're also going to talk in a second about how do we know which order of phase transition, if any, this is. But basically, for you, like in this course, if someone asks you something about critical exponent or like that type of question, unless someone asks you, do you have phase transition, you can assume you have a phase transition. So like second order phase transition. Unless that was like part of the question. So yeah, that may be also like a little bit confusing. That's okay. We're going to solve like another one for like all of the exponents, but this is just a question of like how to get from like the general ugly form that we got to that solution. So the next question we have like we already given by that that form of free energy, and we're going to find all of the four exponents. Any question before we move on?
אנחנו לא רוצים לחפש את כל האקספוננטים הפריטים?
No, just beta for this one. We will do the rest of the exponent in the rest in the.
ולמה הדגשת את ה-AT ואת T-STC ואת 2A-STC בסדר?
I just explained that they're all equal.
כי הם אותו דבר.
Yes. So this is another question from exam that's from 2015. Question 2. So here we have a given form of the free energy. So we have A of t m squared plus b m to the power of 6 plus c m to the power of 8 minus h m. So c, b, and a are like given factors. We don't care about the specific value.
What's the question?
And we need to find all of the critical exponents, alpha, beta, gamma, and delta. So let's start with beta because we already did it, so we know how to do that. So for beta, we take the derivative of the free energy. So df dm, which gives us 2a m plus 6b m to the power 5. Yeah, h equals 0. Plus, we have additional order of m, but we only need the first order, so around m equals 0, we don't care. So this is just higher order, so we take only m and m to 5. So again, one solution is m equals 0, but that's a trivial solution. So for m that's different than 0, we get 2a of t equal minus 6b m to 4. So similar to before, we know that a of t is proportional to t. So this is overall proportional to t. So we have m to the 4 proportional to t, which means that m is proportional to T 1 over 4, namely beta equal 1 over 4.
46.
Hmm?
What is the x?
Where is it? Oh, this is like
Side.
this. No, this is like order of m to the power 7. So I just ignored it because we don't need the higher order. Okay. So this is for beta. Now we do the same for delta. So delta is the exponent for the magnetization. Maybe I write here, so I have more space. So it's go like the magnetic field 1 over delta. So now we obviously cannot take the magnetic field to 0, but we do take the temperature to be not 0, but the critical temperature, because like imagine it like a two-dimensional like phase space, and you can either change the magnetic field or the temperature, and you look at like the dependence of the system on each one of them separately. So what we do here is we take the derivative of the free energy, but this time we take the temperature to be the critical temperature, namely the reduced temperature to be 0. So what do we get? So the first expression, we know that A of t is proportional to t, so this is 0. The first one is the same, just 6 b m to 5 plus, again, some higher order of m, so this is like something of m to 7, so we don't care, minus h. So this is all equal to 0. So we get n to the power 5 equal to the magnetic field, basically over 6 b, but this is just factor. So m is proportional to the magnetic field 1 over 5.
מה ההיגיון לקחת את הפיזיקת טמפרטורה T שווה T?
Sorry?
מה את הרי לוקחת T שווה T?
This?
כן, T שווה 0 זה T, הטמפרטורה שווה לטמפרטורה T.
Yeah, because, okay, so you look around the transition points, so you have like the point that like, you have T equal to the critical temperature and H equal to 0, that's the transition. And you can look at like anything in the system as function of either temperature or the magnetic field. Technically other stuff probably too, but that's what we do. So I look at like small fluctuations, so I look at one variable at a time. So I either look at the temperature and then like I take that to 0 because I move here, or I look at the field and then I take this to be like the critical temperature and like I move in the other. So this is basically the same. Now we have the specific heat and the susceptibility. So they're like tiny little bit different. So I'll just write it here. So m is h1 over 5, and we go out with the temperature was 1 over 4, right? So the exponent of the specific heat is alpha. So C go like T minus alpha. So the specific heat is defined in general like the second derivative of the free energy, right? Where did I write it? The second derivative of the free energy is the temperature. I should have not delete the free energy. So we have second derivative. I already write the reduced temperature, okay, but just after the factor, so it doesn't matter.
How we get this? It's
That's a
Formula.
definition. Yeah.
oh, okay.
So
Also at which equal 0. So also at which
yeah,
equal 0.
this is also for equal 0. So this is the second derivative, and I write here I write it half because I did it. So, okay, so we have derivative by the temperature, but we have something that's depend actually both on the temperature but on the magnetization. And we know the magnetization depends on the temperature. So we can go and use what we already found. That's why you should always find first the magnetization exponents, because then you can use them for that. So we're going to use m go like t1 over 4, and then c is equal to the second derivative of, so a of t is proportional to t, and m squared going to be proportional to t to the power of half. So this is overall t to 3 over 2 plus we have m to the power of 6, so we have 6 over 4, so this is also t to the power of 3 over 2. If we kept the higher orders, we had like m to the power of 8, so this will be like t to t squared. So we see that this is like unnecessarily high order, so we ignore it. So this is basically a second derivative of something that go like t to 3 over 2. So this is approximately going to be t to minus, so first derivative will be t to the power half, second derivative t to minus half. So the specific heat go like t to minus half, which means that alpha is equal half.
רגע, למה עכשיו את מציבה הרי כאילו m שווה t בחזקת הרביעית.
T to m equal to t 1 over 4.
רגע, אז למה זה, למה לא חצי? 3 חלקי 2?
Because you have additional t from here. This is t and this is square root of t.
Okay.
Right, we know that this is always true.
Okay.
יש לדעת מה הסדר הזניח בכל צורך העניין.
You don't have to, but you can take the higher additional order, and then you have something that go like t square, and we know that around the critical t, this will go to 0, so this is like negligible compared. So what else? The susceptibility. So for the susceptibility, this minus gamma. So we can do something similar because we know that the susceptibility can be defined like the derivative of the magnetization in the field. So we know how the magnetization depends on the field, so we can do the same trick. So this is equal to the derivative d over dh of a of t m squared plus b m to the power 6 plus blah blah minus h m. So we know that M go like T1/4. But
לא צריכים את ה-H?
yeah, I just
T minus what? מינוס R?
well
T בחזקת גמא?
yeah, T2 minus gamma. That's the exponent of the susceptibility.
Oh.
Okay, so M go like H to 1/5, so this is H to 2/5 plus B H to 6/5 minus H
לא חסר נגזרת שנייה לאמא?
3/5.
כן. נגזרת שנייה לאמא. את גוזרת את ה-F, אחרי זה לפי H, ואז אחרי זה עוד פעם גוזרת את ה-F.
Oh, okay, that was my mistake. I'm sorry. I felt like something is wrong. So. Thank you. Yeah, okay, so we have two methods to do that. One is to take first the derivative of the free energy and then take the derivative by the field. I also have that in the notes and I mix them up. The first method which I wanted to do is that you just take the derivative of the magnetization, so I don't even need the free energy. So this is just the derivative by the field of the magnetization itself, so we just take that. So this is just H1/5, so this is equal approximately to H minus 4/5. So that's the susceptibility. Now we want to change, but we ask about the dependence, the dependence on the temperature. So we want to change back to the temperature. So this is we're going to change back to the magnetization, and then from the magnetization to the temperature. So H2 minus 4/5, it's like M2 minus 4. And then using beta, so this is using delta, and this is using beta. So this is equal to T minus 1, which means gamma equal 1.
למה נבחר להשתמש בשני? אחד לנחת הטמפרטורה כבר, ושני נחת הסדר, כאילו מוגטי לא אפס.
Yeah, but I did it in like separate states, or separate steps.
Can you explain step by step what you do?
So you can do it like a bit more. I don't know if rigorously is the right way, but you can do it like similar to here. If you take first like the so you have like not equal, sorry. If you have that, so you find the minima of the free energy and take the derivative with the field, and then you isolate the dependence on the susceptibility. But I think this is a bit like longer to do, and this gives you the right result. So I prefer that. So what we did, we say, okay, that's equal to the derivative of the magnetization by the field. So we rewrite the magnetization as function of the field, and then we rewrite the field as a function of the magnetization, and then we rewrite the magnetization as a function of the temperature. So we change to variables, and then we inverse the change. It's a bit weird, but it's like technically just easier.
למה ציינת בצד את שתי הנגזרות האלה, DBH?
That's another way to do that. So,
okay.
So instead of like what we did earlier for the magnetization, we just take the derivative and we compare to 0. But but that will only give us function of the magnetization. So if we want susceptibility, we need to use that, and then every time we have, so this will be like function of the magnetization. So like, and then every time we take derivative of the magnetization field, we use that, and then we get function of the susceptibility. So this is like just another method. I put it in the notes, but it's a bit uglier. So I think that way is just better. So you can all use whatever you feel comfortable with.
אבל נגזרת של F לפי המגנטיזציה אמורה להיות המגנטיזציה? מה זה אומר?
No, this is not equal to something specific. You just find the minima of F. The additional derivative is just so you can use that, because you want to find function of the chi or whatever.
אחרי שמצאת את המגנטיזציה, את המגנטיזציה לצורך מקסימום, את בעצם גוזרת את זה לצורך העניין ב-pH כדי לקבל את הססטיביטי.
Okay, more questions before we go to the last.
כן, quick question. אז עכשיו שיש לך second fast transition, fast transition, אז עכשיו נגיד שואלים אותי על השני והראשון, כאילו, תגיד לי מתי זה הראשון או מתי זה השני.
No, like, okay, I cannot promise that like Ido will not ask something from legal point of view, I guess, but basically like no one's going to ask you about first order phase transition because we didn't study that. I just show you that because now we're going to talk about when do you have second order, so sometimes it's a bit confusing because it looks like something that's in phase transition, but it's not exactly, so just so you see that you have something else, you know. Okay, so now we're going to talk, just a question about when do you have second order phase transition. So that will be, I didn't write which test it is, I think it was also maybe, I don't know. So that question, you have three options.
אם אנחנו אמרנו שאנחנו רוצים לגלות M ספציפי שנותן לנו מינימום, נכון? כאילו מקומום, קישה מערכת צריכה להיות, זאת אומרת ש-M צריך להיות עקרונית קבוע, אבל כאילו גם הוכחנו פה לפי הקשרים שהם הוא לא בהכרח קבוע. תלוי בשדה המקומית.
No, it's not constant, it's not constant in a way that it depends on the temperature or on the field. But it's a constant in a way that for specific field and specific temperature, you have specific value of M.
אוקיי, אז איך אחר כך אנחנו נגיד, הרי אמרנו פה בדרך בצד שאנחנו גוזרים את F ו M, אנחנו מקבלים איזשהו ביטוי, אנחנו מוצאים משם טעים שייתן לי מקסימום, ואז את זה אני רוצה רק לגזור.
Right, that's going to give you the minimum of the free energy, but the M that we find from here is still dependent on the field and dependent on temperature. It's not a constant in a way that it's a constant. It's just a solution.
זאת אומרת, ברגע שאני בעצם עושה את הדבר הזה שמצאת ש-F אני אקבל M כלשהו שהוא תלוי בטמפרטורה ותלוי ב-H.
Yeah, but also, okay, I'll talk about it for 1 second, but like, what happened here is that you have like, for example, so we have like M, A, you take the derivative and you have like A multiplied by M plus B, M to the 5 plus blah blah. So you say, oh, I have the derivative of H, that, I don't find M. I just said that this is 2A and then the M, the H, so this is the susceptibility, plus B, and then I can write the derivative of the M5, the H, as like the H M and the M of M5, like derivative by we're derivative by part kind of thing. So and then you use that and you just need to
פשוט את ה-M שמקיים את ה-T ואת ה-H הספציפיים שמביא את מצאת לא נכון, כי זאת אומרת יש לי T ספציפי, H ספציפי, אני מוצא את M שייתן לי מינימום לאנרגיה החופשית ואז אני יכול לגזור אותו את T ו-H לצורך. אוקיי.
Okay, so So here we have 3 options. We do it like one at a time. We have a given form of the free energy, and it's just like a yes or no question: can we or can we not have a second order phase transition? So
יש מצב שתבדקי את המבחן הזה
yeah, I will put it on the notes.
Okay.
Yeah, I will check. Okay, so the first one is F equal to A of t, m square, b m to 6, plus c m to 19. So that doesn't look suspicious at all. So, okay, so we already know that in Landau theory we only have even orders of the magnetization, except of the only exception is that the is the magnetic field term, but this is not what it is. So we can already like say that it's just not going to give a second order transition, but we can but let's stop for a second and understand why. So if we look at this function, so we usually have, if you remember, we have like a parabola form that when we decrease the temperature we get like two minima, and then we have the spontaneous symmetry built in. But if we look here, it doesn't matter if you look above or below the critical temperature, you're going to have something that's like going like that, and then like it's negative m, it's just going to crash to hell because of that expression over here. So that's like F versus m. So if you look like below the critical temperature, I have 2 minima, and then again it's crashing. So it doesn't matter which temperature I'm going to look at, my minimum point always going to be like minus infinity. So this is like highly unstable system, and we don't have like actually any transition at all. So this is no phase transition.
Sorry, can you ask again the question and the answer?
Yeah, so the question, I will write it.
צריך שיש שתי מינימות פשוט.
So, determine so they either exhibit second order phase transition or they not. And like, of course, if you answer that on the test, you need to like explain why. So that's the first option, and we see that it's not going to work because we have odd order magnetization.
So why would the MH we have a phase transition? Also an antisymmetric function.
I don't know.
MH היא גם פונקציה איזוגית.
Right, that's why I said the only exception of that case is everything that happened to the magnetic field. Because here we look. Yeah, because the magnetic field is going to like when we talk about the phase transition here, we talk about the case where H equals 0, and we look at like it's kind of order that's not supposed to be there. Like it's supposed to be random because they don't have preferred direction, but somehow they choose. So that's what we need.
אז רק אנרגיות חופשיות עם M זוגי יהיה מעבר פאזה.
Yes.
בסדר שני, ואם זה אי זוגי, אז אני אוטומטית אומר, אני רואה איבר אי זוגי כלשהו, אז אני אומר שזה כנראה יהיה...
Yeah, unless it's the magnetic field.
כן.
So we're going to see now that when you have an odd order, you can have two possible options. So this is the first option. The odd order just gave us like we don't have like a stable minimum. So
יש לי גם שאלה.
yeah.
אם החזקה נגיד הייתה ATM בריבוע ועוד BM החמישית ועוד CM בחזקת 18, הסדר הכי גבוה שהיה זוגי טכנית, ואז לא הייתי מקבל פה את ההתנהגות המשוגעת הזו שלי.
But it's still not symmetric.
כאילו אנחנו חייבים שזה יהיה סימטרי כדי שיהיה מעבר כזה בסדר.
So this is A of t, m cube plus b m4 plus cm 8. So
No, here.
right, so we don't have, but what happened here is a bit different than that. So if we look, so this is t smaller than tc and this is t higher than tc. It can be also the opposite, doesn't matter. So in one case, because that multiplied the thing that changed sign with the temperature, so I'm going to have one minima and then like something that's like kind of flat, and here I have the minima here. So this is actually first order wave transition. Yeah, and that's why I mentioned that in the beginning, because sometimes you can have something like that it's like it's technically a phase transition, but that's not what we've been asked. So this is still not going to work.
רגע, זה המסדר הראשון, כי יש פה רק מינימום אחד.
Yeah, but it's because you go from one minimum to another minimum.
כאילו, רגע, ושתיים זה שהיו לי שתי מינימומות ומגיעים לשתי מינימומות מצד שני, כאילו סימטרי כזה?
In second order, you go from one minimum to two minimas, and you have the. So technically, what defines the second order phase transition is the discontinuity of the second derivative. But the physical thing that we were looking at is the spontaneous symmetry working. So you're going to have like the two minima, the system like randomly choose one of them. That's why you have the singular magnetization. But if you're not sure, you can always like just look at the derivatives. But we need like a physical explanation to that.
We need series example for two second order.
What?
את תראי את הדוגמה ל-second order phase transition? או שאין לך?
What do you mean?
נו, כאילו דוגמה גרפית, כאילו.
To second order? Yeah, I can show. It's basically what I showed in the beginning. I showed like first order and second order. I can show again.
רגע, רגע.
אז עוד פעם, מה הנימוק שנתנו פה ללמה אין מפה? כאילו, מבין שיש פה אי סימטריה, אבל כאילו...
Well, as far as it's like, technically you can just claim that we know from Landau theory that this gives us first order phase transition. But you can, if you want to like understand, you can look at how it's looking and you see that it just doesn't look like second order phase transition.
כאילו מבחינת תורת לנדאו אנחנו צריכים לוודא פשוט שכל המקדמים שלנו פה הם זוגיים למעט זה של השדה המגנטי. זה בעצם הכלל היחיד. זה מספיק לי מוקלטת את זה בנפרד? כאילו. אז אם זה לא מסדר שלי זה חייב להיות מסדר ראשון למאמר אחד?
If it's not, no, it can be just no phase transition.
אוקיי, זה חייב פה שזה מסדר ראשון.
Because you have transition from one minimum point to another minimum point.
יש את ציירת.
And we also know from Landau theory that gives us first order, but we don't have to know that. And see. Okay, so here all of the orders of n are even,
So yes.
but we don't have anything that multiply that. You see that like it didn't even put here like constant coefficient to make sure that it's very clear that there is nothing that multiplies. So basically what happened is that we don't have any explicit dependence on the temperature. So if we look at that for like f versus the order parameter, we have for any temperature we just have that. That's it. We don't have any transition. We don't have nothing actually. So no phase transition.
רגע, A של T, הכוונה היא לאיזושהי פונקציה שתלויה
Yeah, we usually
לא
supposed to
constant,
have
לא
here some coefficient that change sign when we go below and above the critical temperature. But here we don't have coefficient that do anything actually, so this is clearly not there. So the two conditions that usually those questions have is one is that coefficient temperature dependence, and the other one is the parity of the exponents. So as far as I remember, those are the two conditions that like show up. Let's hope he will not be like too creative. Which probably like you know that he do the quiz because he's mad that students didn't show up. So maybe you don't want to get him mad before the test. Anyway, so that was it for phase transitions and number theory. I think that's it.
את יכולה להראות צורה גרפית לפייס סקונד פייס טרנזישן?
So this is what we did in the beginning. So if we go to high temperature, we have something that looks like that. So we have a single minimum point, which is, so that means that the minimum point of the free energy is in the zero magnetization, which is the disordered state or phase. When we go to T equal to the critical temperature, this becomes like more and more like flat. And then when we go below the critical temperature, we get to the ordered phase, which is that case, where we have two minima points that are like, they don't look like, but they're in the same height, and then the system spontaneously choose one of them.
המינימות האלה צריכות להיות סימטריות, נכון? קודם כל?
Yeah, they're supposed to be symmetric. I'm just
אוקיי, ואת יכולה לראות בקשר שבו כן יש מעבר אחד מסדר השני?
what?
להראות קשר לדוגמה שהוא מעבר אחד.
Like free energy?
כן.
Well, if we had like that works.
רגע, זאת נוסחה כאילו סוג של מתאימה לזה?
Yeah, that's gonna work for that.
ו-A אנחנו יודעים בוודאות שמשנה סימן כל סופי.
Yeah, if someone like write A of T in that form, you know it's always the same thing.
במבחן גם צריך לדעת הסרטט או שמספיק כאילו...
No, I think just like
כן או לא?
use Landau theory. You need to write something, but I think use Landau theory is like a good argument enough.
Landau theory, okay.
We have a minus sign before the 18. For this example.
If you have what?
Minus sign before a 8. Yeah.
It doesn't matter.
We have phase transitions.
No, because that is basically T minus TC. So you just switch the transition. So you have like that and then that, but it's just a matter of definition. So I wouldn't say it's
רגע, אז כאילו, במקום שהוא יעבור בעצם ממינימום אחד לשני מינימות, הוא יהפוך בעצם הפוך, שבו שני מינימות יהיו שתי גדול מ-TC.
Yeah, from physics point of view, this is a bit weird, but because we used to like ordered case in like ordered phase in lower temperature, so it's not really working. But also you also have like something that multiply that, so maybe A0 is negative. I don't know.
כאילו, אבל מבחינתנו, יש מערכות שכן עושה את הדבר הזה, זה לא נראה כמו מערכות של משהו.
I'm sure people can find out. Like you have phase transition in a lot of weird stuff, like superconductivity and superfluids, and
אז כאילו שהטמפרטורה תהיה יותר גבוהה מטמפרטורה פיזית שלי כאילו שתי מינימות כמו בפרומגנטי, כאילו...
I cannot think about something, but people do weird stuff, so I cannot say it doesn't exist. But the theory doesn't say it.
כאילו העיקר פשוט שהוא עובר ממצב שיש לו שני מינימות למצב שיש לו מינימה אחת. זה העיקר.
You, like the door is over, you can go. I wasn't clear enough. Go away.
Thank you.